Hello, everyone. It's my honor to give a presentation here. I'm Bing Seng from NUS. Today, our topic is Big Data System on Emerging Hardware. In this talk, we actually will talk about our research journey in the last 10 years, and we have an outlook for the next 10 years down the road. So this is outline of my presentation. First, I will introduce emerging hardware and motivate this research. And then we'll talk about our methodology, which is bare metal computing, and which make computing system aware of underlying hardware. And then we talk about our lessons in our journey. And then we conclude this talk and give some future directions. So in the past decades, I think there has been a lot of change in computer architectures, and there are some clear trends. So on the hardware development. So here are some trends we want to discuss, and actually these are the motivations of our research. The first trend is on the processors. As you can see in this figure, we show the bandwidth and also the computation power of the CPU and GPU. As you can see in these figures is that both processors actually grows rather fast, but GPU is even faster. So that's why you can see GPU has been the main accelerators in many supercomputers. The other trend is that you can see the price of the memory and storage have been decreasing significantly in the past years. So this figure really shows the trend that the price of the DRAM, storage, and so on actually decreasing almost like exponentially in the past decades. So this is really important because in big data systems, because the data volume increase, and we actually hope that the working set, the hot data, will not increase so much. And then, given the same budget, we hope the DRAM or storage becomes bigger. Then we can actually hold the working set of the hot data in the main memory. So we hope that to have in-memory processing for big data systems. So that's why we look at processor and main memory. And then you can see in the past decades, I think parallelism and heterogeneity are actually the key developments from CPU to accelerators. And that's why we can see a lot of emerging hardware like multi-core processors, GPU, FPGA, even ASIC are already in the cloud. As long as you have a credit card, you can actually get access to those hardware. And that means actually the access to those hardware becomes very easy. So you can see if you continue the trend, we will see this future hardware we can predict in the next 5 years or 10 years down the road. So from the processor side, we will see the CPU may have more cores, and then more specialized or heterogeneous architecture will be there. It's up to the domain. We have even ASICs for AI accelerations. And we also see changes in storage or memory, particularly non-volatile memory is already in the commodity market. And we already see 3D stacking is emerging. So we will see this as a trend for have of main memory with a larger capacity to terabyte or even more. And also high bandwidth memory is coming. So with hundreds of gigabytes per second. So this is a great improvement and for the current memory hierarchy, which will give a lot of research opportunities. And besides the processor and memory, we have seen some changes in the network side. They are actually faster and cheaper interconnects, such as InfiniBand. And also, we have seen NVIDIA and Mellanox have the integration between GPU and the InfiniBand. So there will be some interesting hardware prototype there. So are we ready for it? I think there are many research opportunities there, despite the past decades of research effort on this. So in our group, we actually try to advocate the concept of pervasive HPC because we 10 years ago, we have this seen the trend of more powerful hardware is becoming more easily accessible and cost effective. So there's a chance that we can build supercomputer or even so-called personal supercomputers with commodity hardwares. So that's why we have the vision. Everyone can perform HPC anywhere and anytime. So in order to achieve that, we want to build a system that is aware of the underlying hardware. So we call it bare metal computing. So this is our research journey. So on one hand, we have emerging hardware as we have introduced just now. On the other hand, we have many big data application and systems. So like relational database, graph, machine learning, and so on. So the interplay between these two dimensions actually generate a lot of system issue like performance, and heterogeneous hardware typically is harder to program. So that's why programmability is an issue, energy efficiency, user interface, and total ownership cost, and so on and so on. There are many research issues there. In order to do that, we actually have a methodology. We call it bare metal computing. So this is actually the methodology we adopt in the group for the past decades. So as hardware evolve all the time, so that's why we actually, in many cases, we start with the benchmarking. So we develop benchmarking with standard benchmarks as well as the emerging workloads from the big data applications. And then we actually do some performance studies and we build models and analyze on the performance behavior. And then I with my students, we have brainstorming and try to have algorithm design and some research on there. And then we will develop a system prototype to demonstrate our idea. So of course, in many cases, this bare metal computing cannot just go linearly. We actually need some iterations, and in many cases, we need many runs of these exercises in order to get our desirable answer. So that's actually, we have explored a lot of interesting hardware in the past, many core processor, GPU and FPGA. And in terms of big data application, we look at relational database, graph, and machine learning, and so on. So, and then we have to deliver a number of publications, but more importantly, we also have system prototypes. So we actually have open source systems. Most of them are in our GitHub webpage. And for example, our recent machine learning library like Thunder SVM and Thunder GBM actually attract a lot of attentions in GitHub and even in the Hacker News headline, okay? And because we have system prototype, we actually deploy those systems in some application as shown here. So it's quite diverse applications. In those applications, we actually typically can improve the execution time by 10 times and or actually reduce the total ownership cost. Okay, so now we pay more time of our lessons in our journeys. So we actually will go through them one by one. But if you are interested in the detail of some of them, feel free to post your questions or email me for more discussion. Okay, the first lesson is that in the past decade, we find whenever we build big data system on emerging hardware, we find this is almost like golden rule. One size does not fit all. So for different hardware, we really need very different architecture-aware software system design so that we can make the system more efficient on the hardware. So of course, due to the parallelism and architectural heterogeneity, we need a better parallelism algorithm design, and also we need to have architecture-aware optimizations. So in the past, we have a lot of these lessons. Typically, those optimization can significantly improve the performance of the systems. So as one example here is that we actually can develop OpenCL based applications on FPGA. So as you can see here, actually the performance difference on this system can be vary about over 2 orders of magnitudes. So it really depends on how you optimize your system on the hardware. Okay, so for more detail, you can refer to the underlying paper. So I won't have time to go through all the details. The other one is that, okay, since one size fits all, and then we cannot really have very different system for every architectures. So laterally, we want to look at the abstractions. So I would say abstractions is very important for building big data systems. And this is even more useful when we building application for irregular data structures. So our methodology is actually on two two folds. One is that we will develop some so-called APIs or abstraction according to the domain. So we develop domain-specific abstractions. So we actually in the past we have developed some very successful open source system, as you can see some of them here. Mars, the map reduced on GPUs. Medusa is a graph processing system on GPU, and also streaming SQL on couple architectures, couple CPU and GPU architectures. So these are some examples, but you can see actually the okay, this is the philosophy. We try to develop the suitable domain-specific abstractions, and behind the abstractions, we try to have the optimizations for those systems, either in compile time, like a static optimization, or runtime optimization. I think we need both under these common abstractions. Of course, as we mentioned in the previous lesson, one size fits all. So usually those optimization need to be customized to different architectures. And so this is the first lesson we learned in the domain-specific abstraction. But something very interesting is that in order to make the system more user-friendly, usually we need to have a more high-level interfaces. It's like in machine learning, we need a Python or scikit interface. So we actually see this in our machine learning library like Thunder SVM. So we do offer like a lot of different APIs here, Python, MATLAB, and so on and so on. So we really we find that in the open source, in the GitHub website, the users actually will raise the issues that do you have the interface for scikit, for example? So in fact, this is very important for the adoption of our systems. So far, this is a very interesting and project which attract over 1,200 stars in GitHub. And also, by the way, it offered the same function to live libsvm, but it's much faster. So that's why we have a lot of users on this library. The other one is the tree-based learning systems. We actually support the GBDT and random forest. It can be 10 times faster than the other libraries. So it's really, this is also being more and more popular in machine learning application. Okay, so, and then the third lesson is actually, since we have very different big data systems, and also we have very different architectures, and the architecture actually keep changing. This is really a challenge. So one of the challenge is that we have legacy software systems. So really the code base is like a monster. As you can see, the numbers here is all millions of lines of code. So the question here is, can we write once and we use for many, many times? Because nowadays, I think the hardware cost is one thing. The other cost is on manpower. I mean, the software engineer. So how we actually will can reduce the cost to develop the application, develop the programs, and maintain the program become a very important issue. So I would say the research on in the past decade is the automatic parallel compilation or optimizer is almost like that in the sense that it's a very challenging topic. So that's why we need some kind of semi-automate tools. We actually, in the past, we explore some compilation framework and even integrate machine learning approach to drive this autopilot system optimizations. Okay, for more detail, you can refer to our publications. Besides the three lessons we have mentioned above, we actually seen other challenges or even risk during our research on building big data system on emerging hardware. So the first one I want to talk about is actually the tracing game between the hardware evolution and also the change of big data systems. So I think that the major problem is the hardware evolves rapidly. So in the past years. So as you can see in this figure, I show you the architecture features introduced to GPU, like a new atomics and unified virtual memory addressing and so on and so on. Okay, so this is really very interesting hardware features happen to the GPU architectures in the past decades. So you can see after the hardware features have been introduced, and then database researchers, including us, we actually propose some optimization on hash join. Okay, so you can see this is the evolution of the hash join, for example. But of course, you can see other operators on this trend also. You can see a lot of interesting evolution on the hash joins. So it really forms a tracing game with each other. So I think there will be a question like, do we really need to trace the hype? I would say yes or no, in the sense that we still get back to our methodology, bare metal computing. So we want to understand these hardware features with the methodology we introduce in bare metal computing. So we want to solve this problem with benchmarks and model analysis, and then we develop some new algorithm and so on to address this problem. So I think this is the way that we solve the problem. And we have been doing this in the past decades on a relational database, graph processing, and so on. Okay. And then the other one I really think is really hard to predict is the whether the hardware is really will be a successful architecture in the market and also in the history. So one thing we have seen is that the database machine, cell processor, Intel names are actually more or less like extinct in the market right now. And our own experience, actually, we pay a lot of attention at the moment that Intel released KNL, Light Landing, and AMD released Fusion. Basically, it's coupled CPU and GPU architectures. So we actually almost the first one to publish research articles on database optimization of big data systems on those hardware. But we realized that, for example, in AMD APU, so far it's mainly for desktop or even embedded applications. And Intel actually more or less like terminate the product line of KNL. So this is really the risk of we do research on big data system on emerging hardware. Okay, so how do we predict the future, right? So how can we look at the opportunities of building big data system on emerging hardware? So from my perspective, I will try to look at the trends in two aspects. On the one hand, we want to look at the trend on big data systems. On the other hand, we want to look at the trend on the computer architectures, and then we look at the interplay between them. So on the big data system, I summarize them as 3 NE, as you can see here. The first one, we see the trend of big data actually moving from enterprise to anyone, because we have seen the big data application system will actually is going to be anyone, in the sense Internet of Things, precision medicines, and so on. So you can see really this is the moving from enterprise to anyone. And we also see the other 2 trends in terms of data. In any form of data, we already see really diversified on a mobile phone. We look at video, text, and so on. And we also see many different kinds of processing, machine learning, and really beyond simple processing. So these 3 NE will continue. So it really makes a landscape of big data system really diverse, and one size that does not fit all will continue. So on the other hand, our look from computer architecture's perspective is really there are many predictions and visions there, but I will see there are some common trend in the predictions. The first one is actually specialized, or the specialized hardware is on the rise because of the cloud, because of the emerging applications. Okay, so we really can, we want to revisit some of the specialized hardware for big data systems, like even graph accelerators, accelerator for large graph processing is actually a very hot topic nowadays. And also because of the emerging application in graph neural network, right? And there are some proposal on going verticals, become 3D stacking, as we mentioned just now, high bandwidth memory, or even more advanced paradigm of processing in memory. So I think this is really interesting topics. And also architecture is, new architecture have been proposed, like quantum computing. So this is really also a direction. We can see big data system in quantum computer maybe in near future. And also machine learning, I think, is create a lot of interesting problem. And also, as I mentioned, we hope that machine learning itself can become part of the solution as well. We want to make the system more automated, driven by machine learning algorithms. But overall, there are massive opportunities for big data system architectures, research on future architectures. So let me conclude this talk. I would say this is really an interesting journey and experience. We hope that hardware and software co-design can enable many interesting system and applications. Thank you.